Chapter 12 looks at something called linear regression and correlation. Basically, we're attempting to answer the essential question, if we have two variables, is there a relationship between the variables? Or better said, how do we determine if there is a relationship between variables? And basically, we're going to restrict our conversation to just linear equations. These are equations of the form y equals a plus bx. And I want to notice this is slightly different than what you saw in algebra, which was mx plus b. Very important here, the b is in a different place, and it means the opposite thing. In statistics, we do it backwards, but our calculator is going to follow this model, so I want to copy the calculator. Where the a is the starting value, the b is the slope, or probably better said, and it makes more sense to call it the rate of change of your data. Now x and y are important too. X is the independent variable, that causes the other to change. And the y, let's do that in a different color. Y then would be the opposite dependent variable, that changes based on the other. So, for example, if a tutor charges her students $25 plus $15 per hour, we would say the independent variable is going to be the hours worked. The number of hours she worked is independent because her hours aren't based on her money. Her money is based on her hours. The hours are independent. They are controlling and changing the dependent variable, which is the money charged. The amount charged depends on the number of hours worked. The hours worked do not depend on the money charged. See how that works? And then if we wanted to make this into an equation, we would say y equals a, the starting value, she starts at $25, plus b, the change, is $15 for every x for every hour she works. So that's your quick crash course review of linear equations. We're going to look at how linear equations could be related to what are called scatter plots, where we use dots to represent bivariate. Bivariate is just a fancy word. Bi means two, variate means variables. Bivariate data. And scatter plots can show us the strength and direction of a relationship. if there is a relationship at all between the two variables. So for example, if I had this scatter plot here where we graphed points all the way up, because they are going uphill, we say that's positive, and because they're in a straight line, we say it's a really strong relationship. There is a strong positive relationship there because it's going uphill and they're really close together. We could have a strong negative relationship that would be going downhill, really close to each other. That is a strong negative correlation. And relationships usually aren't strong. Sometimes they're a little weak. Let's say I've got this data here. It's definitely spread out, but it's definitely going downhill. So it's negative, but it's kind of a weak negative correlation. Yes, it's going downhill, but they're not really grouped together. In fact, it can get so extreme that you start to see data like this. And there, it's not positive or negative. It's very weak. In fact, we will say there is no relationship between the x's and the y's. They're completely random. Where we get into linear regression and testing if there is a relationship between variables is when we start to say, can we draw a line through the data? Finding that line we draw through the data is a process called linear regression, where we find the best fit line. And now the formulas for finding the best fit line are rather ugly looking. They're actually pretty easy to calculate. They just look really ugly and scary. We're going to use our calculator to do all the hard work. So for example, well, actually, before we get to an example, in our calculator we'll put L1 will be the x variables. L2 will list all of our y's, so they'll correspond L1, L2, just like they did for our paired data back in Chapter 10. And then we will run a procedure called, we'll run a statistical test called lin-reg-t-test, the linear regression t-test. And that's going to give us a lot of information that we need to know how to interpret and how to use. One thing it's going to tell us is it's going to tell us t, which is the statistic. It's a student t distribution. T is the statistic of the problem, and that statistic is going to correspond with a p, which is the p-value that we're used to seeing, or the probability that this relationship that we found is purely by chance. Basically, this stuff combines to ask the question, is there a relationship? And we'll get more into that when we talk about how the hypothesis test is run. A, the lin-reg-t test will also tell us an A, which from our y equals a plus bx, A is the y-intercept, or start value. It'll also give us a B, which is the slope, or rate of change. And those two values can work together to help us come up with an equation that will allow us to predict other values. So we'll have an equation from these 2 points that will allow us to predict other values. S is the standard deviation. And we use the standard deviation to help us identify outliers. And the way we're going to find outliers is we're going to add and subtract 2 standard deviations. Anything that's more than 2 standard deviations from our equation, we're going to consider an outlier that needs to be thrown out. R is what we call the correlation coefficient. Which will basically get at how strong and what direction is the relationship. R will be a value between -1 and 1, inclusive. Negative means a negative slope. It's going down as x increases. Positive means the value of y is going up as x increases. Zero, or the closer we are to 0, means there is no relationship. And the closer r is to 1 or -1, the stronger the relationship is. Now this becomes interesting, because how close do you have to be to say we have a strong relationship? Well, to know for sure if we have a relationship in R, we look at the p-value. The p-value is the chance that there is no relationship. The chance this would happen randomly if there was no relationship. Now, if the p-value is small, there must be some relationship. R must be close enough to 1 or -1. Another interesting value to us is if we calculate R squared, which is done exactly like you would expect. You square the R value. R squared is what we call the percent of variation in y explained by the variation in x. In other words, how much changing x is going to affect changing y. What percent of that change in y is because of a change in x? If it's 100%, that means there's a direct relationship. One goes up, the other goes up very predictably. 80%, not so much. There's a little bit of variation that's due to other things, because in reality there's more than one variable affecting each other variable. One thing that's also worth noting, I think I'm on number 3, is when we do a hypothesis test, the null hypothesis will always be that there is no relationship. The alternative is that there is some relationship. In other words, you're going to see H naught is that rho, looks like a capital P, it's the Greek letter rho actually, is equal to 0. And rho is a measurement of the relationship. The alternate hypothesis is always going to be that rho is not equal to 0. And if rho is not equal to 0, then there is some relationship. Strong or weak, there is some relationship that we have established. Okay, enough theory. We're going to bring all of this together with an example. Let's say a professor thinks that he can predict a student's final score based on the score they get on their 3rd exam. The instructor thinks there's some type of relationship here. So the instructor records third exam scores and final exam scores. So the third exam and the final exam. Student gets a 65 on the third, they got 175 on the final. They got a 67, 133 on the final. Got a 71, 185 on the final. Another 71 gives a 163 on the final. A 66 gives a 126 on the final. A 75 earns a 198 on the final. A 67 earns a 153 on the final. A 70 earns a 163 on the final. A 71 earns a 159 on the final. A 69 earns a 151 on the final. Got one more. Another 69 earns a 159 on the final. So we're going to do a whole linear regression and correlation analysis of this data. We're going to make a scatter plot. We're going to do a hypothesis test. We're going to find the formula to predict future values. We're going to see if there's any outliers. We're going to see what predictions we can make. We're going to do it all. The calculator is going to help us organize our information. But first, the null hypothesis is always that there is no relationship, that rho is equal to 0. The alternate hypothesis is that rho is not equal to 0, which means there is a relationship. Let's graph it and try and determine that relationship, if any. First, we're going to enter this stuff into our calculator. The first column, our x variable, we're going to stick into L1. The second column, the y variable, we're going to stick into L2. And if you remember, all that is under Stat. Edit. We've got a lot of stuff in here we need to clear out. So highlight L3, clear, enter. Highlight L2, clear, enter. Highlight L1, clear, enter. And I'm just going to type in L1, the first variable, 65, enter, 67, enter, 71, enter, 71, enter, 66, enter, 75, enter, 67, enter, 70, enter, 71, enter, 69, enter, and 69, enter. Now we'll scroll over to L2 and type in all the corresponding scores. It's important they're in the same order. 175, enter, enter, there it goes. 133, enter, 185, enter, 163, enter, 126, enter, 198, enter, 153, enter, 163, enter, 159, enter, 151, enter, and 159, enter. Now we're ready to do our statistical test. We'll hit Stat and roll over to Test. Down at the bottom, and it's quicker to get there actually if you scroll up, you see ANOVA, and above ANOVA is LinReg T test. We don't want that INT. We're not doing intervals. We're doing a LinReg T test. You could get there by scrolling down, but up was quicker. Hit Enter. And it'll ask us, X list, L1. Yep, we put all of our X's in L1. Y list, L2. Yep, we put all of our Y's in L2. We want to test the null hypothesis that there is no relationship. So make sure the not equal to 0 is highlighted. And then hit Calculate. This is going to tell us a lot of information. I always make sure I write this information down. So that's what we're going to do. We're going to get this information down really quick. T is 2.66. P is 0.026. The degrees of freedom we don't need so much. It's always 2 less because there's 2 variables. 2 less than the number of data values, so 11 minus 2 is 9. A is negative 173.5. Scroll down. B is 4.83. Scroll down. S, the standard deviation, is 16.41. R squared is 0.439, round that to 2 decimals, 0.44. Still scrolling down, R is 0.66. And I think that's it. So a lot of information here. Let's see if we can interpret what's going on. T and P are going to tell us if there is a relationship or not. Notice the p-value is 0.026, and if we don't ask, we assume a 5% level of confidence. 0.026 is definitely less than that, so that probably did not happen by chance. That suggests that there is a relationship. We'll reject the null. There is a linear relationship between the score they get on the third test and the score they get on a final. Now that we know there is a relationship, A and B are going to help us come up with an equation. Remember, y equals A plus bx. When we make our equation, we're going to say y hat, because it's our sample y, is equal to negative A, 173.5, plus 4.83x hat, because it's the sample x. We now have a formula. In fact, let's look at how good this formula is. We're going to sketch a scatter plot of the data, and the calculator actually can do that for us. If we hit second and above y equals, you'll see stat plot, and we'll hit enter on number 1, and you should make sure stat plot 1 is on, and the scatter plot, none of the other options, the scatter plot is highlighted. If that is the case, then what we're going to do is we're going to hit the zoom button, and option number 9, scrolling up might not have been the best choice, should have scrolled down. Option number 9 is zoom stat. Zoom stat will center the calculator screen around your statistics. And when I do, I get this little graph here. And so we're just going to kind of sketch it. You see a few dots down here, some that were right on top of each other. What's interesting is that there was one also up here. So that's my sketch, you know, pretty close to what's going on. If we hit want to put in our equation, we'll hit y equals. And we'll type in our equation of negative 173.5 plus 4.83x. And the x is right next to the stat button. It says xt theta in. And now if I hit graph, it's even going to stick that line of best fit in there. What do you think? Is that a good line? It seems to me it's a little shallow. I kind of feel like I would expect it to go a little steeper. That does seem odd. Possibly because of that one value that seems way out there. Let's test that one value. Going back to our standard deviation. Outliers are plus or minus 2 standard deviations from the equation. So we're going to type in our calculator y1, which is where we typed our equation, plus or minus 2 standard deviations. We actually have to do those separately. Going back to y equals. Scroll down to y2. We're going to tell it to grab that first equation, that y1 equation. It's under vars. Over to y vars, function y1. That's going to take the y1 equation, and we're going to add 2 times the standard deviation. And if you notice in orange, standard deviation was 16.41. Enter. We're also going to do y1 minus, so we go vars over to y vars, function 1, again grabbing y1 again the second time, but this time we're going to subtract 2 times 16.41. And now when I hit graph, what you notice is it gives these other 2 lines. These 2 lines are looking for outliers. We're basically saying acceptable values are inside these 2 lines. And I want to notice this point right here. It looks like it is outside of those 2 lines. In fact, just barely it is above those 2 lines. If I hit trace, I can scroll through the dots. You see one of them has a star on it blinking. Until it highlights that one. I see 65, 175. Looks like it's outside of those lines. So we will say that value, 65, 175, is an outlier. If we delete our outlier, going up to our data, that was our first point, delete the outlier, it might give us better data. So let's do that. We're going to hit stat, edit, and there's that 65, 175. I'm going to delete them both. Delete the 65, scroll over to the 175, delete the 175. Now I only have 10 data values left. Let's see what happens when we run the t-test again. Stat, test, t-test, or it's not a t-test, I'm sorry, it is a linear regression test. The linear regression calculates a t-statistic. Where are we? There we go. Linear regression, t-test. L1 and L2, we're testing that there's no relationship. Let's calculate it. Now look what we have. Now t is 6.29. T is much larger. P, careful, P's not 2.3. Notice the E -4 at the end? That's scientific notation. We have to move the decimal point 4 places to the left. So it's actually 0.0002. A and B have different values now, and the standard deviation is 9.27. R is 0.83. I'm sorry, R squared is 0.83, and R is 0.91. We've got a pretty strong relationship going on here. Let me record this data again. So T was 6.29. The probability was 0.0002. A was equal to -355.19. B was 7.39. S was 9.28. R squared was 0.83. And R equals 0.91. So now when we look at T and P, the probability is so small we can say, yes, there is a very strong relationship. We can see that also in our R value. R is almost 1.0, so this is almost a perfect line going through the points. Our new equation now from A and B, though, is going to be y hat equals A, negative 355.19, plus B, 7.39x. Let's put that in our y equals. I'm going to hit clear on each of these equations, clearing them out. We've already taken care of outliers, so we don't need that anymore. So now in y1, I'm going to type in negative 355.19. Oops, I got out of y1. Now in y1, I'm going to do negative 355.19 plus 7.39x. And now when I graph it, now you see that line goes really right through the middle of that data. And that's going to make it much more accurate in order to allow us to make predictions about data. So let's say if a student earned a 68 on the third test, what would you expect on the final? Well, 68's the score on the third test. That's the x value. So we just have to plug that in. Y is equal to negative 355.19 plus 7.39x. Not x, sorry, it's times 68. And then we grab our calculator. Negative 355.19 plus 7.39 times 68. We would expect them to score around 147.33. What if a student earned a 35 on the test? What would you expect on the final? Well, again, we're going to put that 35 in for the x in the equation. Whoops, got a little excited there with my line. 35 in for that x in the equation. So y would equal negative 355.19 plus 7.39 times 35. Negative 355.19 plus 7.39 times 35 on my calculator is negative 96.54. What happened here? Is that reasonable? Is it reasonable that somebody's going to score a negative 96 on their test? What's going on here? Here's something interesting about linear regression, going all the way back up to my data. Notice my numbers. Let's see, what's the smallest number in there? Is 66, not counting the outlier. And it goes all the way up to 75. Because the data only goes from 66 to 75 as a domain, or our x values, our model really only should be good between 66 and 75. Maybe close to 66 and 75. I might be able to predict 76, 77, those values. But I'm not going to be able to predict much above or much below because my model might break down. So it's important when we're making predictions. 35 is way out there past our data. So it's probably not a good model to predict 35, because what we know is so far removed from this data value. One last thing I want to observe about this data that we did, we aren't touching on it a lot in this course, but I think it's kind of interesting, is r squared, after we removed the outlier, r squared was 83%. That means 83% of the variance in final score was due to the variance in third test score. And I think that's kind of interesting that we can say, hey, 83% of the result is really based on what you got on the third test. Now 17%, the rest of it might be due to other factors, but pretty much 83% of the variance is based on your third test. Kind of neat that we can predict that with our data values. So that's linear regression. Linear regression is going to give us a lot of information that we're going to interpret to make a scatter plot, a line of best fit, find outliers that are 2 standard deviations away, find a formula to make predictions, using R and P, how strong is the relationship, in what direction. A lot of great information. So take a look at the homework and try a few of these. Practice, practice, practice. We'll do some in class, and we will see you then.